The next talk is Frame by Frame, Kernel Streaming Keeps Giving Vulnerabilities by Angelboy from DevCore.
Hello everyone, thank you for coming. I'm happy to have the chance to share our journey into Windows kernel streaming. I'm Angelboy. Currently, I'm working as a senior security researcher at DevCore, focusing on Windows vulnerability research. Today, I will be showing some new bug classes, new vulnerabilities, and ideas for exploration in Windows kernel streaming. Last year, we found multiple vulnerabilities in kernel streaming. Most of them are outbound, along with proxying to kernel. I also presented proxying to kernel at OffensiveCon last year. However, these dozens of vulnerabilities are just the tip of the iceberg. In fact, more and more vulnerabilities are streaming out, and many of them are exploitable. Let's quickly go through kernel streaming first. On Windows system, when you open the webcam or open audio devices such as microphone, the system needs to read or write relay data such as your voice and capture imagery from your device into your RAM. It is essential to read data into your computer more efficiently. Microsoft provides a framework called kernel streaming to handle this data. In kernel streaming, three multimedia class driver models are provided: Port class, AV string, and the string class. Port class is used in audio driver, such as your volume control. AV string is mainly used for video-related purposes, such as your webcam. String class is outdated and rarely used. Due to time constraint, we won't go into detail. If you want to interact with a device like webcam on Windows, you need to create a device just like any other device. For example, open the device and then use IOCTL to interact with it. However, something a bit special here. We need to list devices to see which devices are available in the computer first. These names are not typically like normal device name, but rather something like this one. Each computer is also different. Microsoft provides some setup serious API to help you list the device you need. Case also provides its own API to do this. Actually, this is just a wrapper that combines setup API and the create file. After we open this device, Case will create some kernel streaming related instance, which are kernel streaming objects. This instance will be frequently used, mainly to encapsulate the hardware functionality of devices for developers. Among them, the most important are case filter and the case pin. Case filter usually represent a device or a specific function of a device. When we open an audio device, in most cases, it corresponds to a case filter, which is the green box in the diagram. When reading data from the audio device, it reads into the filter from the left, processes through several nodes, and then output from the right. It usually ends up in your RAM. The points for reading and writing data are called pins. If we want to read or write data, we must open a pin on the filter to create an instance to read from or write to the device. After that, we can use device I/O control to interact with it. You can use this IOCTL to get information about the current variant level. If you want to read from or write to the device, you also need to use IOCTL. After understanding of the functionalities of kernel streaming, we need to understand the architecture and how Windows implement it to find vulnerabilities. Following our analysis, the overall architecture looks like this diagram. After you send an IOCTL request to case device, these are the drivers that might handle your input. Let's talk about KSUNK first. KSUNK is the entry point in kernel streaming. It converts 32-bit request from the WOW64 process into 64-bit request, allowing the underlying driver to handle the request without additional processing for 32-bit request. Another one is case, which is one of the core components of kernel streaming. It is a library of kernel streaming responsible for forwarding requests, such as IOCTL case property, to the corresponding device driver. And it also handles functions related to AV stream. We now have a basic understanding. Let's quickly review the vulnerabilities we discovered last year. Among them, the most important one was the proxying to kernel vulnerabilities. In Windows kernel driver, it's common to rely on the IRP request mode to decide whether to perform security validation. The request mode indicates whether the I/O request comes from user mode or kernel mode. If the request comes from kernel mode, the driver typically skips security check. However, if a kernel driver internally makes an IOCTL call using data controlled by us, then we have a chance to use that IOCTL as a proxy to bypass the security check. Let me use some diagram to show a workflow of a proxying to kernel in kernel streaming. First, we send an IOCTL to interact with the audio device. At this point, the request mode will be user mode, and it will be handled by case sync or directly forward it down here. After sending it to the audio filter, if it is a case property request, it will be handled by case. Case will check whether the property set we provide is supported by the audio filter. If the property is supported and is set with uninitialized set flag, uninitialized property set will be used to handle this property. It will send an IOCTL with our control data again. At this point, the new IRP request mode will become kernel mode. If the subsequent processing relies solely on the request mode to validate the user input, it can be bypassed. For example, the vulnerability we used at Pontoon last year. In case sync, if the request mode is set to kernel mode, no validation is performed. The data provided by the user is directly used as a function call, leading to an arbitrary call. Another example is CVE 2024-30090. In this case, the user provided address is directly used as a kernel arbiter. It can be exploited to achieve an arbitrary memory increment. After we found proxying to kernel, we decided to dive into kernel streaming. This time, we will focus on AV stream-related feature. So, when is AV stream used? It is commonly used with webcam. When you capture a video frame from a webcam, AV stream is involved. It's also used in some audio devices, but webcams are much more common. Over the past year, we have been researching on kernel streaming and found more than 20 vulnerabilities. Around 14 vulnerabilities are related to AV stream, and most of them occur during frame handling. In this talk, we will focus on frame-related issues. Let's talk about kernel streaming frame. So what is kernel streaming frame? In kernel streaming, when reading data from a device, kernel streaming will allocate case frame to store and describe the multimedia data. It also has a frame buffer to store the image data. MDL are used to manage this frame buffer, keeping track of their allocated physical memory, making data access much faster. What is MDL? In the Windows kernel, MDL are mainly used to describe the physical memory mapping of a virtual address. You will often see them using DMA operation and a similar low-level task. MDL are widely used across different components in Windows kernel. They are commonly associated with IRP in the direct I/O, file system, and the network driver during data transfer operations. It is also used in kernel streaming when managing frame buffer. In kernel streaming, an MDL describes a frame buffer that is mapped into user space and a kernel space, and both mapping refer to the same physical memory. As a result, when data is read from the device, it is written to both buffers at the same time. Now, let's talk about how typical application read data from a webcam and how case implement it. Here's a simple overview of workflow of read string from webcam. First, open the device to get a handle. Then create a pin on the filter and get a pin handle. After that, send an IOCTL to set the pin to wrong state. If the device is set to the wrong state, you will see the webcam's lights turn on, which means the camera is now ready. The next step is to use an IOCTL to read the frame from the pin into memory. When sending the IOCTL to read the string, we need to provide a case string header structure as input to specify the necessary information. Kernel will use this information to read data from the device into RAM. The most important fields are the data buffer and the buffer size. Case will map a frame buffer based on the buffer and the size you provide. The data field points to your user space buffer, which will receive the image data. You can also specify an option flag to indicate the attribute of the frame. Let's briefly introduce how case implement reading a frame. First, we need to allocate a buffer in a user space to store the image data. Then we can pass the buffer's address and the size to the kernel using an IOCTL. After we send the IOCTL to webcam, it will be processed by case sync and the case. If the request is not from a WAL64 process, the request will be passed to case. Once case receives the request, it passes the case string header, create an MDL accordingly, and insert it to the IRP. Next, the user buffer will be mapped into kernel space as the frame buffer according to the MDL. At this point, both the user buffer and the frame buffer point to the same physical memory. Finally, case allocate a case frame structure in kernel, which stores the MDL, the kernel frame buffer pointer, and the buffer size. Then the case frame is placed into the queue, waiting to be filled with data. Next, the case worker pulls a case frame from the queue and begin capturing image data from the device into the corresponding frame buffer. If there are other case frame structures in the queue, they will be processed sequentially. Because the user space image buffer mapped to the same physical memory as the frame buffer, it will get the same image data. By the way, we can request multiple frames at once, not just a single frame. Case will create an MDL chain according to case string header array. And then the IRP, along with the frame buffer and the size information, is stored into each case frame structure and placed into the queue, waiting for the worker to capture image data from a device into the frame buffer. Each frame has one-to-one mapping with a string header, an MDL, and a case frame. Now, we have a basic understanding of the architecture and the frame reading. Next, let's shift to attack perspective. Where should we focus on? First one is a transition between case sync and the case. When convert 32-bit request to 64-bit, passing user control header can potentially lead to memory corruption. It might also lead to inconsistency issue. Another interesting target is how case manages frame buffer. If MDL are misused during frame buffer handling, it can lead to various memory corruption issues. We will look at some cases of them. Okay, let's talk about the new bug classes we discovered during our research on kernel streaming. The first bug class is MDL mismatch. When KSUNC receives a 32-bit request, it not only converts the request to 64-bit, but also pre-allocate an MDL for a frame buffer. As shown in this diagram, when we send a 32-bit request, KSUNC will process it first. Then KSUNC will set up the MDL and map the frame buffer. After that, it passes the IRP down to KS for further processing. Since the MDL has already been created by KSUNC, KS will not allocate a new one. Then it will allocate a KS frame to handle the frame. Moreover, if we request multiple frames at once, KSUNC will pre-allocate all the necessary MDL and the frame buffer mapping. However, if the option flag is set to 0x8000, the normal MDL allocation process will be skipped by KSUNC. Actually, the flag is used for MDL caching mechanism in kernel streaming. But I will not detail them here. You just need to know that it causes KSUNC to skip MDL allocation. Moreover, each frame is handled independently. When you submit multiple frames, it's possible to have just one cache. Let me give you an example. Suppose we submit 2 frames, and the second frame has the cache flag. KSUNC will handle it first. KSUNC will check option flag for the first frame. If the cache flag is not set, it will allocate an MDL and map the frame buffer. It then moves on to the second frame. Since the second frame has the cache flag, KSUNC will skip MDL allocation. After that, the IRP is passed down to KS, which will again check the option flag for each frame. Now, the logic is reversed compared to KSUNC. For the first frame, because the first frame doesn't have cache flag, it assumes the MDL is ready and skip it. Then it moves on to the second frame. Since the second frame has the cache flag, KS will allocate MDL and map frame buffer. It then creates cache frame structure based on the order of cache string header entry. Each cache frame is paired one-to-one with its corresponding MDL. They are placed into the queue, waiting for the worker to pull them. But is it really safe? There seems to be some inconsistency. Let's abuse the MDL chain. Suppose we submit 2 frames. For the first one, we set the buffer size to 0x1000 and enable the cache flag. For the second one, we set the size to 0x20000, but we do not set the cache flag. KSUNC will check each header as usual. Because the first frame has a cache flag, it skips MDL allocation. Then it checks the second frame. Since the flag is not set, KSUNC will allocate MDL and map the frame buffer. Next, the IRP is passed down to KS. At this point, KS checks the option flag again. For the first frame, since it has a cache flag, it will allocate an MDL and map a frame buffer, and then insert it to the MDL chain. For the second one, the cache flag is not set. It will skip the allocation. Finally, KS creates cache frame structure based on the MDL chain and the cache string header. The frame size from the header is stored into the corresponding cache frame for both frames. As shown in this diagram, the first frame will have a size of 0x1000 stored, while the second frame will have a 0x20000 stored. Did you notice the problem? After we run it, we got a BSOD. Why? The root cause of this issue is a mismatch between the cache string header and its corresponding MDL for each frame. For instance, the first cache string header might get paired with the MDL of the second frame. While the second case string header gets linked to the MDL of the first frame. What is the actual impact? Now let's walk through the detail and answer the question step by step. As you can see, each case frame created by case is mapped to its corresponding MDL. The frame buffer for each frame is the system VA from the associated MDL. When the worker copies data from the device, it uses the buffer and the buffer size in each case frame to perform the copy operation. The second frame works the same way. The worker refers to the case frame structure to determine where and how much data to copy. However, here's a problem. For a second case frame, the actual buffer size is only 0x1000, but the size in the case frame is 0x20,000. So when the worker uses the size during the copy operation, it attempts to copy 0x20,000 bytes into the small frame buffer. As a result, this leads to a buffer overflow. In fact, several of the vulnerabilities we discovered are related to this issue. If you can find a way to make the case string header and MDL mismatch, you can easily trigger a buffer overflow. The second bug class we are going to discuss is called the forgotten lock in MDL. It is a case of incorrect MDL handling. This bug class is a bit more special. In fact, it is an uninitialized issue in MDL. Let's take a quick look at how MDL are typically used and some common mistakes that can happen around them. The MDL structure is defined as shown here. Star VA usually points to the original user space buffer. System VA is a pointer to the kernel mapping address. The PFN array at the end of the MDL contains the page frame numbers corresponding to the buffer. When the kernel needs to touch user memory, especially under DPC, it often uses an MDL. Typically, kernel invokes the API shown in this diagram. First one is use IO allocate MDL to allocate MDL structure. IO allocate simply allocate an MDL structure based on the given virtual address and the length. In kernel streaming, it will use image buffer and the buffer size as the parameter. The MDL will point to a buffer based on the parameter provided. In kernel streaming, this typically points to an image buffer in user space. Second, it needs to call prop and lock page with MDL to validate and lock the memory page. In this function, it will check if the buffer provided by user is valid according to the access mode flag, and then lock the corresponding physical page in memory. After that, it stores the corresponding PFN into the MDL. This looks just like the diagram. Once prop and the lock page is called, it fills in the PFN array at the end of the MDL, and it also locks the page in physical memory. Third, when the kernel needs to access the buffer, it will call map lock page specify cache. In this function, it will map a new virtual address using the PFN stored in the MDL. By the way, you also can map kernel buffer into user space too. It depends on the parameter of the function. Just like the diagram, after use this function, it will map a frame buffer in the kernel space. It will refer to the same physical address. The last step invoke unlock page and free MDL. This simply unlock the page and release the MDL. I will not go into detail here. Now, I will take a look at a few common vulnerabilities caused by incorrect MDL usage. The first one is the common issue we have been seeing recently. When the kernel uses prop and lock page API to map the memory address provided by the user, it may can incorrectly set the access mode flag. This leads to the failure to check if the address belongs to user space. If the user provides a kernel address, it will map the kernel address to user space. As a result, the user can do arbitrary memory writing in kernel space. Another common issue occurs when a kernel driver free an MDL without clearing the MDL pointer in the IRP. When the IRP is later complete, the system will attempt to free a MDL again, leading to a double free vulnerability during I/O complete. Kernel string has this kind of issue as well. When frame allocation fails, it releases the MDL in the MDL chain, but it does not clear the MDL pointer stored inside the IRP, leading to a double free. These two bug patterns are quite common. There are many more overlooked issues out there. Let's take an example from Microsoft Driver Security Guidance. In this document, Microsoft warned that if developers use map I/O space without validating the physical address, it could lead to arbitrary physical memory being mapped. To illustrate safe usage, Microsoft provides a secure example. First, validate the physical address, and then use map I/O space to map virtual address. Then allocate an MDL for it. After that, call map lock page specify cache API to map a physical address to a virtual address. Now, you might notice something strange here. Where is problem lock page? As we mentioned earlier, in typical usage, after allocating an MDL, you need to call problem lock page or other API to lock the physical page. But in this case, the code called map lock page specify cache directly. This leads to undefined behavior. Here is a quick breakdown using diagram to explain what happened. First, IOllocate MDL is called to allocate the MDL structure and initialize some basic information. However, at this point, the MDL array in the MDL is uninitialized data. If we immediately call map lock page specify cache to map memory, it will still attempt to reference the PFN inside the MDL. It can result in undefined behavior. In many cases, this leads to a BSOD. This kind of mistake happens all over kernel string. Next, I will examine CV 2024-38-38, which clearly demonstrates this issue. We once again create two case string headers, and this time both frames are of the same size. The first frame has a cache flag, while the second one does not. As mentioned earlier, cache sunk will allocate and lock the MDL for the frame that does not have the cache flag. Once that's done, the IRP is passed down to case. Now, let's take a close look at how case handles this frame. If we look at the first while loop inside case, you will see that it checks each case string header to decide whether an MDL allocation is needed. If the cache flag is set, it will allocate a new MDL. Under while CZ4, if an MDL was already allocated, case will call pop and lock page to lock it. But in our case, the first frame has cache flag, and the second one does not. When case begins processing the second frame, it will call case prop string IRP. At this point, the MDL chain inside the IRP looks like this. The first MDL is already locked, but the second one is not locked at all. Then case prop string IRP handles the mapping of frame buffer. It will use map lock page specify cache to do it. If the MDL is marked as lock, the function maps the memory directly, but there is a problem. It only checks the first MDL in the MDL chain, and assumes the entire chain has already been locked. Map lock page specify cache is used on the second. When map lock page specify cache is used on the second MDL, it ends up mapping memory based on an uninitialized PFN list. Does this only lead to a DOS? The good news is that MDL allocated by IO allocate MDL is unusualized in non-page pool. In this diagram, you can see that the PFN at the end of MDL are just leftover memory. As shown here, when IO allocate MDL allocate memory, it allocates pool with uninitialized flag and does not initialize the PFN array in the MDL. This means we can use a spread technique to gain control of the PFN in the MDL. First, we can calculate the size of the MDL that will be allocated. Then we use NumPy to spread a large number of objects to fill memory with control data. After that, we can free some of the NumPy to create a hole in a non-page pool. Next, when IO allocate MDL is called, it will reuse those free regions. The PFN array inside MDL will now contain a value from our NumPy object. When map log page specified cache is called afterward, it will regard those controlled PFN as a very physical page, and map length as a frame buffer. Finally, when the worker copy image data from the device, it's write directly to physical address we controlled. Actually, not all PFN can be mapped. They must be valid, such as a resident page. But that's already enough for what we want to do. That is, we have an arbitrary memory right now. The next step is to achieve EOP with arbitrary physical memory right. At this point, the primitive is powerful enough, but where to write? Interestingly, when we test on 24H2, we noticed that the physical page of NT was always at 0x1004000 in many environments. We test it on Hyper-V and VMware. It might be different now, but it's still likely to be a fixed value. So does that mean we can just write directly to NT and take over a kernel? There's a problem. We cannot control the data coming from the webcam. At first, it looked like we were stuck, but a stable arbitrary physical write primitive is quite powerful. So we went back, reviewed the full workflow carefully, and eventually found a new angle of attack. Kernel streaming offers a feature called buffer mode. When a case frame is being created and the buffer flag is set, case will allocate an additional buffer and emit as an intermediate buffer. It then copy the content from the original image buffer into the new buffer memory. After the device finishes copy its data, or if an error occurs, case copy the content of the buffer memory to the frame buffer in the kernel space. Let's say we spread MDL and submit frame with the buffer flag. Case will allocate a buffer and copy in our data. Then we force a failure in a later frame to interrupt streaming. Case will copy the content of the buffer memory back into the frame buffer. However, this frame buffer has already been mapped to a physical address of NT image. In other words, we now have an arbitrary physical memory write with fully controlled data. This opens the door to directly modify kernel code. For our exploit, we chose to override a security check inside open process. We replace the privilege check for SE debug privilege with SE change notify privilege. And now, any normal user can open any process except PPL. OK, let me demo it. This exploit is running on 24H2. And I use a normal user with webcam. Then run exploit, and spray MDL, and terminate the stream. You will get a citizenship. OK, sync. There are multiple ways to cause this issue in kernel streaming. As long as you find a way to make it forget log page, it can result in arbitrary physical memory writing. Okay, the last issue we would like to share is frame buffer misalignment. But before diving into that, we need to introduce a case object in kernel streaming, the case allocator. Through case allocator, a set of frame buffer can be pre-allocated and reused, reducing the overhead of dynamic memory allocation during streaming. Typically, an allocator object is assigned to a pin, and the third-party driver can implement their own custom allocator if needed. Case also provide a default allocator. In general, you can create a case allocator using the case create allocator API, and configure it using a structure called case allocator framing, such as the number of frame buffers and the size of each buffer. You can also specify the alignment for each frame buffer. In fact, we need to provide an alignment mask for it. Let me use a diagram to walk you through this. When a pin is open, the kernel creates a pin object. Then we can create a case allocator and attach it to the pin. Before reading data from the pin, we need to set a state to the run. At this moment, the allocator will pre-allocate the number of frame buffer we have configured. From that point on, data is streamed from the device into pre-allocated frame buffer. Corresponding case frame structures are also allocated. When we send an RCTL to read the data, the process begins just like we described earlier. However, instead of reading from the device each time, the worker will copy data from the pre-allocated frame buffer. Today, we will focus on how default allocator manages pre-allocated buffers. Let's take a deeper look at default allocator. When we call case create allocator, case create a default allocator and initialize it using the parameter we provide. Internally, case implement its own allocation function. It also uses a Lookaside list to measure the buffer efficiently. The allocation function is quite simple. It just calls exallocate pool to allocate memory. If an alignment mask is specified, case adds a 4-byte value representing the padding size in front of the frame buffer. Then in a free routine, case uses this padding size to calculate the original pointer returned by exallocate pool. As shown in this diagram, the memory layout of the pool looks like this. The purple region represents the padding, and the blue region is the frame buffer. The 4 bytes just before the frame buffer are used to store the padding size. Under normal case, the alignment mask should be a power of 2 minus 1. However, here's the problem. Case only check whether the alignment mask is greater than 0xFFF. If it's less than 0xFFF, it accepts any value, even if it's not a valid alignment. That is, we can submit any value less than 0xFFF. At first glance, this might seem like a useless bug, just a minor memory alignment issue. But what happens when that misaligned buffer meets the Lookaside list? Lookaside lists are per processor cache optimized for fixed size memory block. It uses a simple singly linked list. Allocation and free always check the list first before using the general pool. That means when we allocate a frame buffer, it will be taken from the list. And when we release a frame buffer, it will be inserted back into the list. Another property is that Lookaside list entry must be 0x10 byte array, aligned. As you can see, In the allocation logic, before returning a chunk, the kernel aligns the return chunk address to 0x10. Similarly, when freeing memory back to the Lookaside list, it also aligns the chunk. As shown in this code snip, the free routine aligns the first entry in a list. So what happens if a frame buffer that's not 0x10 byte aligned is placed into a Lookaside list? Let's play the funky frame. We write a script to list out all possible alignment masks and the padding size. Here we are using an alignment mask that give us 8 bytes of padding. Then we configure the allocator to pre-allocate 4 frame buffer. The buffers will look like this one. Due to the padding, the buffer's address will all end with 8. After that, the allocator gives us 4 buffers, A, B, C, and D, all of which have address ending in 8. When these buffers are freed, Cache releases them one by one, and insert them into the Lookaside list in order. First, we free frame buffer A. It gets inserted into the Lookaside list normally. Next, when we free B, the allocator first aligns the current head of a list, which is frame A. Then it sets the next pointer of frame B to point to list aligned frame A. And insert B at the head of the list. We continue by freeing frame C, which follows the same pattern. Finally, we free frame D. In the end, the Lookaside list will look like the layout shown in this diagram. Have you spotted this issue? The issue is in the next pointer of frame D. Due to misalignment, the next pointer points to the start of the pool chunk, rather than the frame buffer. As shown in this diagram, you will notice the next pointer of frame C points to padding area, which stores padding size. When viewed as a 64-bit value, this pointer becomes something like 0xA and A0, which is an address in user space. Our plan is to allocate a memory page at 0xA and A0 to gain control of the list, and have the final node point to our target address. After that, when the device reads data, Cache will write the data into those buffers. In theory, this gives us an arbitrary memory writing, right? However, we still face the same problem as before. We cannot control the content that we want to write. It also cannot use buffer flag in this case. At this point, we were stuck again. But after thinking it through one more time, we found another way. Let's abuse the Lookaside again. As shown in this diagram, we first construct a fake linked list in user space. The address 0x414100 represents a user control memory address. Then allocate the frame buffer. It will align the chunk and update the list head. However, because the alignment logic treats the start of the frame D as a next pointer, once the first chunk is popped from the list, the linked list transforms into what you see in this diagram. Next, we allocate all the chunks from the Lookaside list. We also configure the allocator to use smaller frame buffer, which causes the webcam enter a wait state. It will not read data from the device. Next, we trigger a stop to release all of the frame buffer. At this point, Cache starts returning the buffer to the Lookaside list one by one. First, it will release a frame D. Then it will free the malicious chunk at 0xA and A0. After that, it free the fake chunk at DOX4141 or. In the end, it will release our target address. As a result, the target address of next pointer will point to DOX414100. In other words, we can write the address of our chunk into the target address. This value can be any user space address. That is, we now have arbitrary memory writing. We turn a useless bug into a powerful vulnerability. After we gain arbitrary memory writing on Windows 23 H2, we can use anti-security system information to leak straight up address. Then we flip the bit for token privilege. Now we can use any well-known technique to achieve EOP. Okay, let me demo it. We test it on 23H2. I also use a normal user with webcam and allocate for buffer, then terminate it. You will get a system again. Okay, thanks. The next. This bug pattern may not only appear in kernel streaming. By paying closer attention to MDL-related issues, you might be able to discover many more bugs in other drivers. Takeaway: kernel streaming is a valuable research target, and likely still contains many undiscovered vulnerabilities hidden inside. Understanding Windows API implementation and the layer misuse risk is key to find vulnerability and exploitation. Keep this pattern in mind. It might be your next vulnerability. Okay, thank you for listening.